Right now, as you're listening to this, something from another star system is tearing through our cosmic neighborhood at 137,000 miles per hour. It's being hunted, not by aliens, not by some distant civilization, but by us, a swarm of Earth spacecraft scattered across millions of miles, are tracking an ancient comet older than most stars you've ever seen. They're watching it get ripped apart by the sun's fury, documenting its slow disintegration as it races toward its doom. This isn't a mission we planned. It's an interstellar encounter happening right now, in real time. And what we're learning is rewriting everything we thought we knew about where planets come from. Scientists call it 3I Atlas. It's the third messenger from the void to visit our solar system. And by the time you wake up tomorrow morning, it might be gone forever, or torn into a million pieces by forces we're only beginning to understand. Subscribe CTA. Hit subscribe if you want to fall asleep to the universe's deepest mysteries. We're exploring the cosmos every week, and trust me, you don't want to miss what's coming next. Now, let's chase this interstellar stranger together. On July 1st, 2025, in the high deserts of Chile, a robotic telescope system called Atlas was scanning the night sky. It was doing what it always does, hunting for asteroids that might threaten Earth. That night, it found something else entirely. A dim speck of light, moving wrong, not in an ellipse around our sun, like everything born in this solar system, but on a hyperbolic path, a one-way ticket through our cosmic neighborhood, traveling faster than anything gravitationally bound to our star could ever move. The astronomers checked their calculations 3 times. Then they checked the archives. Pre-discovery images going back to mid-June confirmed what seemed impossible. This object, this visitor, came from interstellar space. They named it 3I Atlas, the third confirmed interstellar object in human history. Only 2 others had ever been detected before. The first, Oumuamua, appeared in 2017, that mysterious cigar-shaped thing that tumbled past us. The second, Comet Borisov, in 2019, a more typical icy wanderer. But 3I Atlas. It was different from both. When discovered, it was screaming inward at around 137,000 miles per hour, reaching speeds up to 152,000 mph at its peak. That's fast enough to cross the entire United States in 20 seconds. Its hyperbolic excess velocity of 58 kilometers per second relative to the Sun proved it would never return. Picture this. An object has been traveling through the darkness between stars for possibly billions of years. Cold, silent, alone. Then, almost by accident, its path intersects our solar system. Gravity from the Sun bends its trajectory inward, and for a few precious months, we get to see it before it vanishes back into the void forever. But here's where the story gets strange. Initial observations suggested the comet's nucleus was massive, far larger than expected. Estimates from Harvard astrophysicist Avi Loeb put its mass at over 33 billion tons, with a diameter exceeding 3 miles. This made it somewhere between 1,000 to 100,000 times more massive than the previous 2 interstellar visitors. That shouldn't be possible. Statistical models of interstellar object populations predict that smaller fragments, things the size of buildings or city blocks, should be thousands of times more common than kilometer-scale giants. By those estimates, astronomers should have detected hundreds of thousands of smaller Oumuamua-like objects before encountering one as large as 3I Atlas. Yet here it was, a cosmic anomaly, a statistical impossibility that refused to care about our predictions. From Hubble Space Telescope observations, astronomers determined the comet's nucleus diameter was somewhere between 440 meters and 5.6 kilometers. Even the lower estimate would make it enormous compared to typical interstellar visitors. The question haunted researchers. Why did we find the giant first? Between May and September 2025, 3I Atlas showed no measurable non-gravitational acceleration, the kind caused when a comet's outgassing creates thrust. Most comets wiggle slightly as jets of gas push them around. Not this one. The lack of acceleration implied the nucleus must be especially heavy. With a mass exceeding 33 billion tons, it was moving like a bullet through our solar system, massive and unstoppable. But size wasn't the only mystery. When scientists turned their most powerful instruments toward this ancient wanderer, the James Webb Space Telescope, Hubble, NASA's newly launched SphereX mission, they found something unexpected in its chemical signature. The comet exhibited an unusually high ratio of carbon dioxide to water, unlike most comets from our own solar system. Observations detected it outgassing carbon dioxide, water, carbon monoxide, cyanide gas, and atomic nickel vapor. During observations, the comet developed a striking green glow. That green luminescence? It comes from diatomic carbon, molecules of two carbon atoms bonded together, glowing emerald when energized by solar ultraviolet radiation. It's a signature of specific chemistry, specific conditions, specific origins, and those origins pointed to something extraordinary. Scientists analyzing 3I Atlas's composition believe it likely originated from the Milky Way galaxy's thick disk, a region associated with star formation during what astronomers call cosmic noon, approximately 9 to 12 billion years ago. Let that sink in for a moment. This object speeding past Mars right now might have formed when the universe was less than a quarter of its current age, when our sun didn't exist yet, when Earth was still billions of years from forming. ATD could be a frozen time capsule from an era when our galaxy looked completely different. But that ancient chemistry is only the beginning of this story. To understand what 3I Atlas truly represents, we need to travel back in time, back to cosmic noon, when the Milky Way was young and wild. Imagine the Milky Way galaxy 9 billion years ago. Our corner of space doesn't exist yet, not as we know it. The thin disk where our solar system would eventually form is still assembling itself from gas and dust. But higher above and below the galactic plane, in what astronomers call the thick disk, star formation is already ancient history. This is where 3I Atlas might have been born. The thick disk represents an earlier generation of the galaxy, stars that formed when the Milky Way was young and wild. Back then, during cosmic noon, galaxies across the universe were manufacturing stars at rates 10 to 100 times faster than today. It was the peak era of star formation in cosmic history, when the universe was most alive with stellar birth. The chemistry of that era was different too. Stars in the thick disk formed from material with lower metallicity, fewer heavy elements like iron relative to lighter elements. They had decreased fractions of iron peak elements, but increased abundances of alpha process elements like oxygen, magnesium, and silicon. And critically, they likely had higher water content. 3I Atlas carries that signature in its composition. The high carbon dioxide to water ratio detected by James Webb and other instruments tells a story about where this comet formed relative to its parent star. Carbon dioxide only freezes into solid ice beyond what astronomers call the CO2 frost line, a distance from the star where temperatures drop low enough for carbon dioxide to condense. This means 3I Atlas formed in the cold, outer reaches of its original planetary system, but it also formed hot. The presence of certain minerals and the specific chemistry suggest formation in an irradiated environment, a place bathed in radiation from a young, active star. This would mean that supervolatiles like molecular nitrogen or carbon monoxide were largely driven off during formation, leaving behind the water and carbon dioxide we see today. Think about what had to happen for this object to be here now. First, it formed in a protoplanetary disk around some star we'll never identify, 9 to 12 billion years ago. It grew large, massive enough to survive what came next. Then something catastrophic happened, perhaps a close stellar encounter. Perhaps gravitational chaos as giant planets migrated through the young system. Whatever the cause, 3I Atlas was violently ejected, thrown out at such speed that it escaped its star's gravity entirely, and then it wandered. For billions of years, it drifted through interstellar space. The galaxy rotated beneath it. Stars formed and died. Entire planetary systems came into being, evolved, and perhaps developed life, all while 3I Atlas coasted silently through the void. Research suggests it may have passed within about 3 light-years of 25 known stars during the past 10 million years. Each time, a near miss, close enough that if those stars had planets, beings on those worlds might have seen it as we see it now, a fleeting visitor in their skies. But those close approaches weren't close enough to capture it. It kept going, its trajectory shaped by the cumulative gravitational influences of every star it passed, every dense molecular cloud it skirted, every subtle tug from the galaxy's overall mass distribution. Until finally, in 2025, its path brought it here. The chemistry frozen inside 3I Atlas represents conditions that don't exist in our solar system. Our system formed 4.5 billion years ago from material already enriched with heavy elements from previous generations of stars. We're made of recycled stardust from dozens or hundreds of earlier stars. But 3I Atlas might come from an era with fewer recycling cycles. Its parent star could have been a relatively low metallicity star, forming from gas that hadn't been enriched as much by supernova explosions. The ratios of elements in that gas would have been different. The chemistry of planetesimal formation would have followed different rules. This means 3I Atlas isn't just a comet. It's a sample of ancient galactic conditions, a messenger from an era of the Milky Way that we can study no other way. We can't travel back in time 9 billion years. We can't visit the thick disk directly to see what star and planet formation looked like back then. But when an object from that era happens to pass through our neighborhood, we get a glimpse. The green glow, that diatomic carbon, fluorescing in sunlight, is light from molecules that might have formed in the outer disk of a planetary system that predates Earth by twice Earth's current age. The water vapor streaming off its sun-warmed surface might be ice that condensed when the universe was less than 5 billion years old. Every measurement we take, every spectrum we capture, every observation of how it responds to solar heating adds to our understanding of how planetary systems formed under those ancient conditions. And what we're learning suggests something remarkable. The processes that build planets might be more universal than we thought. Despite forming under different chemical conditions in a different era of galactic history, 3I Atlas still looks fundamentally like a comet. It has ice, it has rock, it outgasses in predictable ways as the sun warms it. The universe, it seems, has been building the same types of objects for billions of years. Across vast differences in time and space and chemistry, the fundamental physics of how ice and rock clump together in protoplanetary disks remains consistent. But there's a deeper implication here, one that changes how we think about planetary formation itself. If 3I Atlas was ejected from its birth system 9 billion years ago, and if similar ejections have been happening constantly throughout galactic history, then interstellar space must be filled with these wanderers, trillions upon trillions of them, drifting between the stars, occasionally passing through planetary systems like ours. And if they're passing through, sometimes they get captured. And that's when something extraordinary could happen. something that might explain how giant planets form, how worlds are born, and why we're here at all. Here's the frustrating thing about interstellar visitors. We can't chase them. Not really. Not with current technology. When 3I Atlas was discovered on July 1, 2025, scientists immediately began calculating whether any spacecraft could intercept it. The answer was brutally simple. No. Any probe launched from Earth after the discovery date would require a delta V, a change in velocity, of at least 24 kilometers per second to reach the comet. That's beyond the capability of any propulsion system we currently have. Even if we'd known about 3I Atlas before its discovery, a spacecraft launched on July 1st would have needed about 7 kilometers per second of delta V to still, impossibly difficult with our existing rockets and propulsion technologies. Launching from Mars would have been more feasible. A probe departing Mars between July and September 2025 would have required only about 5 kilometers per second to reach 3I Atlas in early October. But we don't have mission-ready spacecraft sitting on Mars waiting to launch. We barely have rovers there. So instead of chasing, we're watching. And as it turns out, we're watching from everywhere. Over the past few decades, humanity has scattered its eyes across the solar system. Not intentionally for this purpose, these spacecraft were built for other missions, designed to study other worlds. But they're out there, positioned at different vantage points, equipped with cameras and spectrometers and particle detectors. And when an interstellar visitor passes through, they can all turn their instruments toward it. Near Earth, the Hubble Space Telescope was first to get detailed images. On July 21, 2025, when 3I Atlas was about 277 million miles from our planet, Hubble captured it in stunning detail. The images revealed a teardrop-shaped cocoon of dust streaming from the nucleus, the characteristic coma of an active comet. The James Webb Space Telescope observed it on August 6 with its near-infrared spectrograph. Webb's infrared vision could detect the chemical fingerprints of molecules in the comet's coma and tail, revealing that composition that set 3I Atlas apart from other comets. NASA's SPHEREX mission observed the comet between August 7th and August 15th, adding even more spectroscopic data to help astronomers understand what this ancient object is made of. But those were the easy observations. Spacecraft, near Earth, looking at something millions of miles away. The real opportunity came when 3I Atlas's trajectory brought it deeper into the solar system. On October 3, 2025, the comet made its closest approach to Mars. It wouldn't come particularly close by human standards. About 30 million kilometers separated them. But for spacecraft already orbiting Mars, 30 million kilometers is close enough. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter were ready. These missions, designed to study the red planet's atmosphere and surface, turned their instruments skyward. Mars Express's high-resolution stereo camera and ExoMars TGO's color and stereo surface imaging system, both typically used to photograph Mars, attempted to capture the interstellar visitor. The spectrometers on both spacecraft, Mars Express's Omega and SPECAM instruments, and TGO's Nomad spectrometer, aimed at the comet to measure the spectrum of light streaming from its coma and tail. If the comet was bright enough, these instruments could reveal details about its volatile activity and composition from a perspective impossible to achieve from Earth. Even the Mars rovers got in on the action. NASA confirmed that Curiosity and Perseverance, robots on the Martian surface, would attempt to observe 3I Atlas at night during the period when it was closest to the planet. From the ground, they might detect changes in the comet's brightness and watch its coma evolve as solar heating increased. The Emirates Mars mission's infrared spectrometer was also positioned to gather data, adding another set of eyes to the growing observation campaign. But Mars wasn't the only vantage point. Further out, the European Space Agency's Jupiter Icy Moons Explorer, JUICE, had perhaps the best seat in the house. Between November 2nd and 25th, as 3I Atlas emerged from its closest approach to the Sun, JUICE observed it with multiple instruments, cameras, spectrometers, and particle sensors all turned toward the comet. And the timing was perfect. This was when 3I Atlas would be most active, most dramatic. Perihelion, the closest point to the Sun, occurred around October 30th. After that date, the comet would be superheated, outgassing violently, its tail streaming millions of miles behind it. JUICE would see it in that state, blazing and brilliant. The only problem? JUICE is far from Earth and currently using its high-gain antenna as a heat shield against the Sun. It's transmitting data back through a smaller medium-gain antenna at a much lower rate. Scientists don't expect to receive JUICE's observations of 3I Atlas until February 2026, but the wait will be worth it. JUICE's instruments can detect things Earth-based telescopes can't from that position in space, at that particular moment in the comet's journey. Even the Parker Solar Probe got involved. This spacecraft, designed to dive closer to the Sun than any probe in history, was positioned to observe 3I Atlas with its WHISPER instrument from late September through early November. Parker could watch the comet as it plunged toward perihelion and then whipped back outward, a perspective from the inner solar system that complemented all the observations from further out. The Psyche mission, currently traveling to study a metal-rich asteroid, passed relatively close to 3I Atlas on September 4th. It's unclear if it captured observations, but the possibility exists. ESA's Hera mission, en route to study the aftermath of NASA's DART asteroid impact experiment, also had an opportunity to glimpse the interstellar visitor. Altogether, it's an unprecedented observing campaign. More than 15 spacecraft, scattered from Earth orbit to Mars to Jupiter to the inner solar system, all coordinating to study a single object that will never pass this way again. This is what modern space exploration looks like. Not a single grand mission, but a network of instruments working together, combining perspectives from across vast distances to build a complete picture of something moving too fast for any one observer to fully capture. It's humanity's distributed eye, watching the cosmos. But what if we could do more than watch? What if, next time, we were ready not just to observe from millions of kilometers away, but to actually intercept an interstellar visitor? That's the dream that researchers like Dr. Hiroyasu Tsukamoto have been working toward, and the technology already exists. Dr. Hiroyasu Tsukamoto, a professor in the Department of Aerospace Engineering at the University of Illinois, has been thinking about this problem for years. How do you intercept something moving at tens of kilometers per second when you don't know exactly where it's going to be? Interstellar objects are among the last unexplored classes of solar system visitors. They hold information about primitive materials from exoplanetary star systems, chemistry and composition we can't study any other way. But they pass through our solar system only once at incredible speeds, and we usually discover them with only weeks or months of warning. Traditional spacecraft guidance systems aren't designed for this. They assume you have time to plan, calculate, course correct. They assume you know where your target is going to be. Interstellar objects don't cooperate with those assumptions, so Tsukamoto developed something new. Neural-Rendezvous. It's a deep learning-driven guidance and control framework designed specifically for autonomous encounters with extremely fast-moving objects. At its core, it uses contraction theory for non-linear control, mathematical techniques that provide probabilistic bounds on how close a spacecraft can get to its target, even when that target's position is highly uncertain. The system doesn't need perfect information. It doesn't need humans sending commands from Earth. It works autonomously, in real time, adjusting the spacecraft's trajectory based on what it observes as it closes in. But here's the insight that makes it revolutionary. One spacecraft isn't enough. Even with Neural-Rendezvous guiding it perfectly, a single probe has maybe a 50-50 chance of getting a clear view during the flyby. The speed is too high. The uncertainties are too large. One spacecraft means one angle, one set of instruments, one opportunity to get the data you need, and if it fails, if the probe passes too far away, or if dust blocks the view at the critical moment, or if a critical instrument malfunctions, you've lost your only chance to study an object that won't return for millions of years. So Tsukamoto and his team proposed using a swarm. The concept is elegant. Instead of one spacecraft desperately trying to hit a moving target, you deploy multiple spacecraft, call them deputies, that work together. One spacecraft, designated as the chief, coordinates the swarm. But each deputy operates autonomously, guided by its own Neural-Rendezvous system. Before the encounter, the swarm distributes itself across the region of space where the interstellar object is most likely to pass. Picture an ellipsoid, a three-dimensional oval stretched along the object's probable trajectory. The deputies position themselves at strategic points across this ellipsoid, each one covering a different volume of space. As the interstellar visitor approaches, each spacecraft continuously updates its trajectory based on new observations. The Neural-Rendezvous framework calculates the optimal path to maximize its chances of a close encounter while coordinating with the other deputies to ensure comprehensive coverage. It's like casting a net across the probability space. If the object passes closer to one deputy, that spacecraft gets the best data. But the others are still close enough to gather valuable information from different angles. Multiple vantage points mean multiple spectra, multiple images, multiple data sets that can be combined to build a complete picture. The swarm approach also provides redundancy. If one spacecraft fails, if its instruments malfunction, or if it's damaged by micrometeorites during the years-long cruise to the intercept point, the others continue the mission. You're not putting all your eggs in one basket. Tsukamoto's team tested the concept using M-star multi-spacecraft simulators and tiny drones called crazy flies. These drones, originally designed for indoor swarm demonstrations, became stand-ins for spacecraft in the tests. The results were impressive. The swarm successfully positioned itself to maximize information gathering, even when the target's trajectory was uncertain. Two undergraduate students, Arnab Hardwaj and Shishir Bhatta, worked with Tsukamoto to develop the mathematical framework for optimally positioning multiple spacecraft during an ISO encounter. Their research looked at how to maximize the information gained from the encounter using formal probabilistic guarantees. The key question was, given multiple spacecraft, how do you optimally position them to maximize what you learn? The answer involves information theory. Each position in space provides a certain amount of information about the target. Some positions reveal more about composition, others about structure, others about how the object is outgassing. The swarm's positioning algorithm calculates which arrangement of deputies maximizes the total information gained, accounting for uncertainties in the object's position and the fact that some spacecraft might get better views than others. It's optimization in real time, happening autonomously as the encounter unfolds. The framework has been published in the Journal of Guidance, Control, and Dynamics. It's not science fiction. The mathematics have been proven. The simulations have been run. The drone tests have validated the basic concepts. What's missing is the actual deployment. Spacecraft waiting in strategic orbits, ready to intercept the next interstellar visitor when it arrives. Imagine how different the 3I Atlas encounter would have been with a swarm already in place. Instead of watching from millions of kilometers away, spacecraft would have flown directly through the comet's coma. They would have sampled the outgassing material, measured the composition up close, photographed the nucleus from multiple angles, detected any magnetic fields or charged particles. We would know whether 3I Atlas is a single solid body or a loose collection of fragments. We would see surface features, craters, ridges, smooth plains, exposed ice. We would watch in real time as solar heating drives jets of gas from specific locations on the nucleus, and we would gather that data not from one perspective, but from several, building a three-dimensional understanding of an object from another star system. The technology exists. The framework is ready. What's needed now is the will to deploy it, to station a swarm of spacecraft in the outer solar system, waiting patiently for the next interstellar visitor to arrive. Because they will arrive. The Vera Rubin Observatory, coming online soon, is expected to discover hundreds of interstellar objects every year, each one a potential target, each one carrying secrets from distant stellar systems. The era of passive observation is ending. The age of the swarm is beginning, but before we send spacecraft to intercept visitors, there's something else we need to understand about 3I Atlas. Right now, as it races toward the Sun, it's under attack, and what's happening to it reveals the violent beauty of cosmic encounters. On September 24, 2025, something violent happened to 3I Atlas. The Sun attacked it. Not deliberately, of course. The Sun doesn't target specific objects. But it erupted, a massive coronal mass ejection, a billion-ton cloud of plasma, and twisted. Magnetic fields hurled outward at over 2 million miles per hour. And 3I Atlas was directly in its path. Coronal mass ejections, CMEs, are among the most powerful events in the solar system. They occur when the Sun's magnetic field lines become so twisted and stressed that they suddenly snap and reconfigure, flinging enormous quantities of charged particles into space. When a CME hits Earth's magnetic field, we get auroras and sometimes disruptions to satellites and power grids. When a CME hits a comet, something much more dramatic happens. The comet's tail gets ripped off. This isn't speculation. Astronomers have watched it happen before. In April 2007, NASA's Stereo spacecraft observed Comet Encke as a CME slammed into it. The wave of solar material struck the comet head-on, and within hours, Encke's ion tail, the narrow, bluish tail formed by charged particles, completely disconnected from the nucleus. It was spectacular. One moment, the comet had a tail. The next moment, the tail was drifting away independently, a ghostly streamer of plasma no longer connected to its source. But the effect was temporary. Within minutes, a new tail began forming as the comet continued outgassing. The CME had passed, and normal solar wind resumed pushing the new material away from the nucleus. I Atlas experienced something similar, but potentially more intense. For one thing, Encke's encounter happened during solar minimum, the quiet phase of the Sun's 11-year activity cycle. Solar storms were rare. CMEs were weak. But in 2025, we're near solar maximum. The Sun is active, covered in sunspots, erupting frequently. And 3I Atlas is passing much closer to the Sun than Encke did, just inside Mars's orbit, into the inner solar system where solar wind is dense and solar radiation is fierce. The CME that struck 3I Atlas in late September was likely faster and more magnetically complex than the one that hit Encke. The interaction would have been more violent. Here's what probably happened. The CME, a magnetized cloud of plasma, raced outward from the Sun, overtaking the slower-moving solar wind. At its leading edge, a shock wave formed, like the bow wave in front of a boat. This shock compressed and accelerated the ambient solar wind, creating a region of intense pressure and tangled magnetic fields. When this shock hit 3I Atlas, It slammed into the comet's coma and tail with enormous force. The comet's ion tail is made of charged particles, ions and electrons, created when ultraviolet radiation from the sun strips electrons from gas molecules in the coma. These charged particles are sensitive to magnetic fields. They flow along magnetic field lines in the solar wind, creating the narrow, straight ion tail that always points directly away from the sun. But when the CME's shock wave arrived, it brought its own magnetic field, much stronger than the background solar wind, and oriented in a different direction. The sudden change in magnetic field direction caused the ion tail to kink, twist, or disconnect entirely. At the same time, the CME's dense plasma pushed against the comet's coma like a headwind, compressing it on the sunward side and creating ripples and disturbances visible in photographs. Observers watching from Earth reported that 3I Atlas brightened significantly during this period. The increased brightness came from enhanced outgassing, the comet responding to the extra energy and pressure from the CME by releasing more gas and dust from its nucleus. Spectroscopic observations showed the green glow intensified. That diatomic carbon fluorescence became more pronounced as solar UV radiation, carried by the CME along with the plasma, energized more molecules in the expanding coma. But what makes this encounter scientifically valuable isn't just the drama. It's what we can learn from it. When a CME interacts with a comet, the comet becomes a probe. It samples the CME's structure, revealing details about the plasma density, magnetic field strength, and composition at that location in space. By watching how the comet's tail responds, how it bends, breaks, or reforms, scientists can infer properties of the CME that are difficult to measure directly. It's like dropping paint into a flowing river. The patterns the paint makes reveal the currents and eddies in the water. For 3I Atlas, this was especially valuable because it's an interstellar visitor. Its chemistry is different from solar system comets. The way it responds to solar radiation and solar wind might be subtly different, revealing whether comets from other stellar systems behave the same way as our homegrown variety. Early observations suggest they do. Despite its exotic origins, 3I Atlas acts like a typical comet when the sun heats it. It outgasses, it forms a coma and tail. It responds to CMEs the same way Encke and other solar system comets do. This tells us something profound. The physics of comets is universal. Whether an icy body formed in our solar system 4.5 billion years ago, or in a different planetary system 9 billion years ago, when you heat it with a star's radiation, it behaves predictably. But the sun wasn't done with 3I Atlas. As the comet continued its plunge toward perihelion, solar heating intensified. At the distance where 3I Atlas was discovered, beyond Jupiter's orbit, sunlight is weak, and the comet was cold and relatively inactive. But as it moved inward past Mars's orbit, solar radiation increased dramatically. The sun's light follows an inverse square law. Get twice as close, and you receive 4 times the radiation. By the time 3I Atlas reached perihelion on October 30th, solar radiation was hundreds of times more intense than when it was first spotted. That kind of heating does things to a comet. The ice doesn't just sublimate slowly, it erupts. Jets of gas burst from cracks and fissures in the nucleus. Dust gets carried aloft. The coma expands to millions of kilometers in diameter, and sometimes the stress becomes too much. The comet doesn't just lose its tail, it loses itself, fragmenting into pieces as internal forces tear it apart. Which brings us to the most dramatic form of destruction a comet can experience. Not from external attack, but from its own rotation. There's something you need to understand about comets. They're not solid, they're fragile, porous, more like piles of gravel loosely held together by ice than like solid boulders. When you heat them, When you spin them, when you stress them, they fall apart. And 3i Atlas is spinning. Every comet rotates, some slowly, taking days for a single rotation. Others spin fast, whirling around their axis in just hours. The rotation comes from the way the comet formed. Collisions and gravitational interactions during the chaotic early days of its birth system imparted angular momentum that the E object has carried ever since. But rotation creates problems. As a comet gets closer to the Sun, its surface heats up. Ice turns to gas, sublimation, the direct transition from solid to vapor without melting. This gas doesn't escape uniformly. It jets out from specific locations, fractures, pockets of volatile ice, regions where the surface is thinner or darker and absorbs more heat. These jets act like rocket engines. Each jet pushes against the nucleus, creating thrust. If the jets are arranged asymmetrically, and they usually are, this thrust makes the comet spin faster. It's called outgassing torque, and it's a death sentence for loosely bound objects. Imagine a pile of icy rubble held together only by its own weak gravity and the frozen adhesion between chunks. Now make it spin faster and faster, while simultaneously heating it so the ice turns to gas and the structure weakens. Eventually, centrifugal force overcomes gravity. The comet flies apart. We've watched this happen multiple times. Comet 73P Schwarzmann-Wachmann 3 began fragmenting in 1995. By 2006, Hubble Space Telescope images showed the B fragment continuing to break into smaller chunks. The photographs revealed a hierarchical destruction process, fragments breaking into subfragments, which broke into even smaller pieces, all streaming down the tail like a trail of breadcrumbs. Some chunks were house-sized, others were barely detectable. They were pushed down the tail by their own outgassing, like miniature rockets. The smaller chunks had less mass, so the gas pressure accelerated them faster. Over just a few days, some chunks dissipated completely, evaporating into invisible vapor. Comet Atlas C 2019. Chai 2019. Y4 disintegrated in April 2020. Hubble captured the breakup, the nucleus fragmenting into more than 30 separate pieces in just 3 days. Observers watched in real time as a bright, condensed head rapidly became diffuse and dim, a sure sign the nucleus had shattered. Comet C 2024 G3 Atlas. A different Atlas comet, not our interstellar visitor, survived a close perihelion passage in January 2025, but then began falling apart days later. The nucleus held together during the brutal solar encounter, but couldn't survive the aftermath. Astrophotographers captured the transformation. The bright, compact head dissolving into a soft, diffuse glow as fragments separated and scattered. The cause of these breakups isn't always clear. Sometimes it's rotational stress, the comet spinning itself apart. Sometimes it's thermal stress, the rapid heating and cooling as the comet moves closer to and then away from the Sun, creating cracks that propagate through the structure. Sometimes it's internal pressure. Gas trapped beneath the surface, unable to escape quickly enough, builds up pressure until the structure fails catastrophically. A cometary explosion from within, and sometimes it's simply structural weakness. These objects aren't engineered. They're piles of rubble that happen to stick together during formation. Any flaw, a large void, a weak layer, a concentration of volatile ice becomes a failure point under stress. So the question hanging over 3i Atlas is, will it survive? There are reasons to think it might. That enormous mass, 33 billion tons, suggests a nucleus that's more cohesive than typical. The fact that it showed no measurable non-gravitational acceleration between May and September means its outgassing isn't strong enough to significantly push it around. That implies either the outgassing is weak or the nucleus is so massive that the jets can't budge it. A massive, coherent nucleus should be more resistant to breakup than a small, fluffy one, but mass alone doesn't guarantee survival. Comet Hale-Bopp in 1997 was enormous by cometary standards, and it still showed signs of extreme fracturing, multiple jets, violent outbursts, behavior suggesting it was barely held together. Gravitationally, the researchers studying 3I Atlas noted that it falls into what they call the damaged region of the stability diagram, a mathematical space where comets are predicted to be, fractured internally but still gravitationally bound. These are objects on the edge, held together more by gravity than structural integrity. If that's accurate, then 3I Atlas might be a rubble pile after all, just a very massive one. Chunks of ice and rock pressed together, held by the weak grip of mutual gravitation, spinning slowly through space. And now, the sun is heating it. Jets are erupting. Thermal stresses are building. Each rotation brings different parts of the nucleus into sunlight, creating temperature gradients that expand and contract the material. October 30th was the moment of truth. Perihelion, closest approach to the sun, maximum heating. If 3I Atlas was going to break apart, that's when it would happen. But here's the beautiful irony. Even if the nucleus shatters, even if it fragments into a dozen or 100 pieces, the comet doesn't truly die. Not immediately. The fragments continue on similar trajectories. They stay close together, bound loosely by gravity, moving as a cluster. From a distance, the comet might look the same. The coma might even get brighter as the increased surface area allows more ice to sublimate. It's only over time, days, weeks, months, that the fragments separate. Some pieces outgas more than others, pushing themselves onto slightly different paths. Eventually, they drift apart, each becoming its own tiny comet, each following its own trajectory out of the solar system. Astronomers call them headless wonders, comets that maintain their tails even after the nucleus has disintegrated. The dust forming the tail was expelled before the breakup. It continues drifting outward, pushed by solar radiation pressure, creating a ghostly tail with no head attached. If 3I Atlas fragments, its pieces will scatter along its orbital path. Future astronomers, centuries from now, might detect individual chunks still following the same hyperbolic trajectory out of the solar system. A trail of breadcrumbs marking where the ancient visitor passed through. And those fragments? They don't just vanish. They become something else. They distribute themselves. They seed the cosmos, which leads us to one of the most mind-bending theories in planetary science, that destruction like this might actually be how new worlds are born. Dr. Susanne Pfalzner of Forschungszentrum Jülich has been thinking about a puzzle in planetary science. Giant planets shouldn't exist, or rather, they shouldn't be as common as they are. The traditional model of planet formation, planets growing slowly through collisions of smaller objects, has a problem. It's too slow. Protoplanetary disks, the swirling clouds of gas and dust around young stars where planets form, only stick around for a few million years. After that, the star's radiation blows the gas away. Giant planets need that gas. Jupiter and Saturn are mostly hydrogen and helium captured from the disk. If you want to build a giant planet, you need to form a large rocky core fast enough to gravitationally capture gas before the disk dissipates. But the traditional growth process runs into problems at intermediate sizes. When boulder-sized objects collide at high speeds, they don't stick together. They bounce or shatter. It's called the growth barrier, and it's a major obstacle in planet formation theory. So how do giant planets form? Pfalzner's answer is radical. Maybe they cheat. Maybe they get a head start. What if young planetary systems capture interstellar objects like 3I Atlas, massive pre-formed chunks of ice and rock, and use them as seeds for rapid planet growth? The concept is elegant. A young star surrounded by a protoplanetary disk passes through a dense region of the galaxy, a molecular cloud, or a star-forming region, where interstellar objects are common. Some of those objects encounter the disk. If the conditions are right, the disk captures the interstellar visitor. The object settles into orbit within the disk, embedded in the gas and dust. And then it starts collecting material. Because the interstellar object is already large, kilometers across, billions of tons, it has significant gravity. Dust and pebbles in the disk are attracted to it. They spiral inward and stick to its surface. The object grows. Normally, you'd need millions of years for collisions to build something that size. But with an interstellar seed, you skip that step. You start with a massive nucleus and grow outward from there, sweeping up material much faster than traditional accumulation. This could solve the timing problem. With a big enough seed, you could build a giant planet's core in hundreds of thousands of years instead of millions. Fast enough to capture gas before the disk disappears. Falzner's models show it's plausible. Simulations predict that young protoplanetary disks could capture millions of interstellar objects over their lifetimes. Not all would be large enough to serve as planetary seeds, but even a small fraction could make a difference. And there's observational support for the idea. Giant planets are more common around more massive stars heavier than our Sun. Traditional planet formation theory struggles to explain this. Massive stars have shorter-lived disks because their intense radiation blows gas away faster. That should make giant planet formation harder, not easier. But if giant planets grow from captured interstellar seeds, the pattern makes sense. Massive stars are more common in dense star-forming regions where interstellar objects are abundant. They're also more gravitationally influential, with larger capture cross-sections. A massive young star in a crowded stellar nursery might capture dozens or hundreds of large interstellar objects, providing multiple seeds for rapid giant planet formation. Our Sun formed in a less dense environment, probably in a smaller star-forming cluster. It would have encountered fewer interstellar objects, captured fewer seeds, and ended up with fewer giant planets as a result. The 3I Atlas discovery adds weight to this theory. The fact that we found such a massive interstellar object suggests large visitors are more common than previous detections indicated. If objects like 3I Atlas regularly wander through the galaxy, then young planetary systems must encounter them frequently. And if they're encountering them, some fraction must be captured. Think about what this means. 3I Atlas might be the kind of object that seeded giant planet formation in some distant stellar system billions of years ago. It was ejected from its birth system, wandered through space, and maybe came close to being captured by another star's protoplanetary disk. But it wasn't. It kept going, through the galaxy, through billions of years, until finally it arrived here. Now imagine the reverse scenario. Imagine an object like 3I Atlas, but billions of years ago, when our own solar system was forming. The young Sun, surrounded by a disk of gas and dust, an interstellar visitor passing through, captured by the disk's gravity, settling into orbit. Could Jupiter have started as an interstellar seed? We don't know. There's no way to test it directly. Jupiter's interior has been processed by billions of years of heat and pressure. Any signature that might have revealed an interstellar origin is long gone. But it's possible. The chemistry would fit, the timeline would work, and it would explain how Jupiter grew large enough to capture gas before the solar nebula dispersed. This is the deeper meaning of destruction in the context of interstellar visitors. When 3I Atlas fragments, if it fragments, it's not just breaking apart. It's distributing itself. Some pieces will escape the solar system entirely, continuing their journey through the galaxy. But others might end up on different trajectories. Some might be captured by the Sun's gravity, settling into long, elliptical orbits in the outer solar system, new members of the Oort cloud. Some might eventually collide with planets or moons, delivering their ancient ice and rock to worlds that formed much later. And in other stellar systems, at other times, similar objects, ejected from their birth worlds, captured by new protoplanetary disks, might become the cores of new planets. Destruction and creation intertwined. The object destroyed is the world created. The planetary system that violently ejects its comets provides the seeds for new planetary systems light years away. It's cosmic recycling on galactic scales and billion-year timescales, a cycle where no object is ever truly lost, just redistributed, repurposed, transformed, and witnessing that transformation, capturing it in those fleeting seconds of encounter, is what the spacecraft swarm would make possible. Imagine 3I Atlas right now, in this moment, as you listen to these words. It's already past perihelion. The sun is behind it. It's climbing back out of the solar system, accelerating as the sun's gravity flings it outward. A cosmic slingshot sending it back toward the darkness between stars. By late September 2025, it had become too close to the sun to observe from Earth. The comet moved into the solar glare, the bright glow that drowns out fainter objects. Ground-based telescopes couldn't see it anymore. Even Hubble and Webb lost track. This is when the spacecraft scattered across the solar system became our only eyes. The Mars orbiters watched in early October. Parker's solar probe observed from its extreme position near the sun, and JUICE positioned perfectly to see the comet in its most active state after perihelion, collected data that won't reach Earth until February 2026. In early December, 3I Atlas was predicted to emerge on the far side of the sun. If it survived perihelion intact, it would become visible again to ground-based telescopes. Fainter, more distant, but observable. Astronomers marked their calendars. Telescopes were scheduled. When the comet appeared, if it appeared, they would be ready. And it would be different. After perihelion, comets are changed. They've been baked by the sun. Outer layers have sublimated away. Some volatiles have been exhausted. The nucleus might be smaller, its activity declining, or it might be more active. If perihelion cracked the nucleus and exposed fresh ice beneath. Or it might be gone, fragmented into pieces too small to observe individually. We won't have the complete story for months. Patience is required in astronomy. You plan observations years in advance. You wait for the right moment. You collect data. Then you wait again for transmission, processing, analysis. The universe operates on its own timescale. But while we wait, scientists are already analyzing what's been gathered. Hundreds of observations from dozens of telescopes and spacecraft, thousands of images, spectra covering wavelengths from ultraviolet through visible to infrared. They're measuring rotation rates, tracking the evolution of the coma's size and brightness, analyzing spectral lines to identify molecules and determine isotope ratios, modeling the dust tail to understand particle ejection. Every piece of data is a clue. Every measurement constrains the models. Slowly, a complete picture of 3I Atlas emerges. Not just what it is, but what it tells us about the conditions that created it billions of years ago. Preliminary results are already appearing. Papers on preprint servers, conferences scheduling sessions, researchers debating interpretations. Was it really from the thick disk? Could it have originated from a different stellar population? What does its chemistry imply about its parent system? How typical or atypical is it compared to solar system comets? The discussion will continue for years. Even after 3I Atlas has left entirely, scientists will still be analyzing its data, extracting new insights, comparing it to future interstellar visitors, because there will be future visitors. The Vera Rubin Observatory is preparing to begin operations. When it does, its massive mirror and sensitive detectors will scan the sky night after night. Early estimates suggest Rubin might detect dozens or even hundreds of interstellar objects per year. We're entering an era where interstellar visitors won't be rare, once-in-a-decade events. They'll be routine, expected, catalogued, and with that routine will come better opportunities. More advance warning. Time to plan coordinated observation campaigns. Time to position spacecraft for optimal viewing. Maybe, eventually, time to deploy that intercept. Swarm. The study of interstellar objects is transitioning from opportunistic astronomy, taking whatever data you can get. When a rare visitor appears, to systematic science, our atlas is both an ending and a beginning. The third confirmed interstellar visitor and the herald of hundreds to come. As it speeds away from the sun, accelerating back toward interstellar space, it leaves behind something more valuable than any physical sample we could have collected. It leaves knowledge. In a few months, it will cross Mars's orbit again, heading outward. In a year or two, it will pass Jupiter's orbit. After that, it enters the realm of the outer planets. Saturn, Uranus, Neptune, vast gas giants orbiting in the cold darkness. And then, beyond Neptune, it leaves our planetary system entirely. It crosses into the Kuiper Belt, that distant region of icy bodies. It passes through without slowing, without interacting. Beyond the Kuiper Belt lies the heliosphere's outer boundary, the heliopause, where solar wind loses its battle against interstellar space. Voyager 1 and 2 cross that boundary, becoming humanity's first interstellar emissaries. IE Atlas will cross it too, probably within a few years, and when it does, it will be truly gone, beyond the sun's influence, back in the realm between stars where it spent most of its existence. Its journey will continue, not for years or decades, but for millions or billions of years. It will drift through the galaxy, pulled gently by passing stars, nudged by molecular clouds, slowly tracing an orbit around the galactic center. Maybe, billions of years from now, it will encounter another stellar system. Maybe it will be captured, torn apart, scattered into fragments that rain down on alien worlds. Maybe it will become a seed for new planet formation. Or maybe it will just keep going, forever, through the endless dark. We'll never know. We lose track of it long before any of that happens. Within months, it becomes too faint to observe. Within years, it's too distant for even our most powerful telescopes. But it doesn't matter, because what remains isn't the physical object. Atlas taught us that the galaxy sends messengers constantly, pieces of other planetary systems, crossing paths with ours more often than we realized. It taught us that these visitors carry information from environments we can't study any other way. Ancient stellar populations, thick disk chemistry, conditions during cosmic noon. It taught us that our spacecraft network can adapt to study unexpected targets, coordinating observations across vast distances, and it taught us what we need to do next. The swarm concept isn't science fiction anymore. Neural-Rendezvous exists. The mathematics work. The simulations succeed. The technology is achievable. With Vera Rubin about to begin operations, we'll have advance warning. Objects will be spotted months earlier. That buys time. Time to calculate trajectories, position spacecraft, plan encounters. We could fly through the coma of the next visitor. We could sample the outgassing directly. We could photograph the nucleus from dozens of angles. We could measure things impossible from distant observation, and each encounter would add to the database. Each visitor would expand our understanding of galactic chemistry, planetary formation, the distribution of building blocks across the Milky Way. Eventually, we'd build a census, not of stars or planets, but of the wanderers between them. the orphaned fragments of planetary formation, the building blocks that didn't make it into planets but got thrown out into the galaxy. That census would reveal things we can barely imagine. How common is water in other stellar systems? How much organic chemistry happens in outer protoplanetary disks? Are there exotic chemistries we've never seen? And underlying all of it is a shift in how we think about our place in the cosmos. We're not isolated. The solar system isn't separate from everything else. We're connected by these ancient wanderers, by the seeds they might have provided, by the universal physics that governs how worlds form. Atlas came from somewhere else, somewhere ancient, and for a few months it was here with us. We watched it, we studied it, we learned from it, and then we let it go, back into the darkness, carrying its secrets forward into whatever comes next. As you drift toward sleep tonight, picture that ancient wanderer, still racing outward, its tail fading, the sun shrinking behind it to just another star among countless stars. Somewhere in the galaxy, another comet is beginning its own journey inward toward a different star. And somewhere, perhaps, beings not unlike us are preparing their own telescopes, their own spacecraft, waiting to glimpse their own interstellar visitor and wonder, as we do, what secrets it carries from the cosmic deep. If this journey through time and space brought you peace tonight, consider subscribing. We explore the universe's deepest mysteries every week. Black holes that devour galaxies, planets where it rains diamonds, moons that hide oceans beneath frozen shells, each story designed to help you drift off while wondering about the infinite. Sweet dreams, stargazer. And remember, somewhere out there, ancient messengers are still traveling, still carrying the galaxy's oldest secrets, waiting for someone to notice them passing by.